Okay, so let's begin with the task that we gave last time, was to show that for the harmonic oscillator, any operator can be written as sum of products of creation annihilation operators. And there I made a mistake last time just to say that this matrix element is not equal to 0 only if Q is equal to N, P is equal to M. That's not true. And so if P minus Q equals, sorry, what did you say?
P minus Q will be M minus N, I think.
M minus N. Then, and you need another condition also, right? That.
But M and N is greater than P and Q. Mod M, I mean, yeah, they're positive. So
M, N.
Greater than P and Q. Like, so M is greater than P and N is greater than Q. Or greater than equal to, I think is.
Yeah. Okay, let's see that, whether that is true or not. Suppose you have N is equal to 3, P, Q is equal to say 1, P is equal to say 2, and M is equal to 4.
Yeah.
Right. But 4 minus 3 is equal to 2 minus 1. So let's see if this is a non-zero element. So when you act once A hat on 3, you get 2, and 4 minus 2 is also 2. So you will get a non-zero matrix element, right? Excellent. So basically you have to take into account a lot of terms, and therefore it is a little bit more complicated, as you correctly noted. Yeah. All right. So yes. Okay, so anyway, but anyway, you should be able to write it this way, where OMN it is a much more complicated object. So this OMN is not the matrix elements, but something else, right? I mean, well, we have to see. So there is a way to do this. Maybe it's a good idea if somebody writes it down, how to do it. It might be useful for later purposes. But we will have a simpler way to do things later. So. But for the moment, I just want you to realize that it is always possible to do it. So now let's see something important. So why harmonic oscillators are important? Or why QFT is just a sum of interacting harmonic oscillators? Well, the answer is, in a way, is embedded in classical physics. But of course, it's not a good idea to start from classical physics and justify things, because a good thing to do would be to not to start from quantum field theory. Sorry, not to start from classical physics and go to quantum physics, but rather the other way around. That is something we will be doing soon. Okay, that was something that I will be doing at some point. But for the moment, let us start from the classical point of view and try to see why. So suppose you have a system of n particles, x1 to xn, right? There are n particles, and you all know, and they have, and for the moment, think of it like a non-relativistic system, and they have some kind of a potential which is very complicated. So it is 3n dimensional. It's a 3m dimensional space, because for each n particle you have 3 positions, and in this complicated dimensional space you have some minima where xi is equal to xi naught, where v is extremized, right? Where v has a minimum, which means that v prime del xi, v prime at xi is equal to xi naught is equal to, so if it's a vector, I should just, sorry, that's true, let me, I'm sorry. Let me do it this way. Let me put it I stands for the particle index and is equal to xi naught. And then I say that grad I v when xi equals xi naught is equal to 0, and then this matrix grad I grad j v xi equals to xi naught. So this matrix has to be has a positive has positive eigenvalue. Okay, so that's the assumption that we're taking. So it means that it is a stable minimum. And when you diagonalize this matrix, right, you get the normal modes, right? So there is some combination Q, right, QA, which is simply some, let us say small QA I xi, right, where you sum over all the particles. So these are the normal modes which satisfy this kind of equations, right? This is always true. You can always take any system, and if the system is stuck somewhere here in the minima, you can always write it as sum of normal modes, right? So classically, the Hamiltonian can be written in this way: sum A half QA dot square plus omega A square QA square, right? I'm just absorbing the mass and everything inside this Q to have the right dimensions.
So that's minus omega A square.
No, it's
plus.
Hamiltonian. So it's
no,
Hamiltonian.
Sir, the equation.
Right. So this is plus. Sorry. Okay. So I would put it this way. So it's basically a sum of harmonic oscillators, right? Now there comes something. There are two things that has to come in here to get field theory out of this, or just even a classical approximation. The first thing is that okay, suppose this potential has many minima like that, right? So for example, you can take a crystal. The crystal can have many possible minima, right? And if you're stuck somewhere, there will be a huge barrier to climb and go there, right? So statistically, it might be a very hard process, because if you have read statistical mechanics, then climbing this barrier is not easy. I mean, that's fine. But what you can show in both statistical physics and classical physics is that if you have quantum mechanics, and it's true both in classical mechanics and quantum mechanics and statistical mechanics, the point is that if you're in quantum mechanics, for example, there is, if you have if you have finite number, if n is finite, then actually there is only one ground state, typically, not many ground state. Yeah, sometimes you can have more than one, but typically it is finite, not the infinite number. Even if the potential itself has, many minima, the number of ground states are typically small. That's because of tunneling, right? You can tunnel from one to the other, and there's amplitudes, and they mix these things, and therefore only a linear superposition of being here and there is actually a true ground state of the system. However, when n goes to infinity, this tunneling is suppressed, as something like e to the power minus n. And in a thermodynamic limit, essentially we can just think about being stuck somewhere and just live there. I mean, there is absolutely no way you could go to the other one. It's a highly, if you take the strict thermodynamic limit, of course, in reality, thermodynamic limit is only an approximation, but it's a very, very good approximation, right? If you take a crystal. So because if you have 1 mole atoms and it is suppressed by 1 mole, then e to the power minus 1 mole is extremely tiny number. It's like e to the power minus 10 to the power 23, right? It's an extremely tiny number. 1 mole has 10 to the power 23 particles, for example. Okay, so then or 1 gram of hydrogen atom. Even 1 gram, you can apply the thermodynamic limit. So you are then stuck here, right? You are stuck here, and then and therefore it's a good thing just to think about this and nothing else, right? This is the first thing that comes even when you quantize the theory, or you want to think of a statistical ensemble. Anyway, so this is one thing. The second thing that comes in mind, comes here, is that if you look at any, if you look at sufficiently dense system, right? If it's sufficiently dense, like you take particles anywhere, so there is always some kind of emergent quasi-translational invariance. So, for example, if you form a crystal, it will not be exactly translational invariant, but it is invariant up to some discrete translations. So this emergent translational invariance comes about, right? If you look at the system at sufficiently large scales. For example, the universe is not homogeneous, right? The universe, like if you look at here, there is one galaxy, then you go like several light years, like 100 light years or so, then there is another galaxy. So it's not homogeneous, but if you look at some kind of a huge length scale, and if you look at like where every dot is a galaxy, there is something called this scale is the scale of homogeneity of the universe, I think, is 100
parsec. 100
yeah,
parsec.
exactly, 100 parsec. And what's a parsec? Do you remember?
I forgot. So I don't remember.
Yeah, it is a few light years. I mean, let me quote the number.
3 into 10 power 16 light meters. That is okay. Wait, I'll see in light years.
Yeah, in light years, I think 100 parsec. If you look at this at such enormous scales, then you see that the universe simplifies and you have some homogeneity, right? Now,
So
emergence
3.26 3.26 light years.
3.26 light years
is one parsec.
Light years. Yeah. So that is the rough scale. So basically, it covers several. Like you have to look at very large length scales, and then the universe looks homogeneous at such 100 parsec, right? So it is 300 light years roughly. So and then now why it is emerging? It is essentially emerging because of laws of probability. So laws of probability simply tell you that it is extremely difficult or extremely rare configurations will not be homogeneous at certain beyond a certain length scale. So of course, the probability should not be typically taken as such, because the system also tries to minimize energy, and it has to be weighted as such. But laws of probability and statistical mechanics essentially tell us that at some level, there will be some kind of homogeneity, quasi-homogeneity. Quasi-homogeneity means that, okay, we'll see what you mean by quasi-homogeneity. But let us say it is exactly homogeneous. That's a good approximation. Then you have QA, but this QA actually forms a continuum, right? So one way to write this QA would be, it would have a mode which is K, which is basically the wave number, and then it would be some discrete index, which I call A. So it would look something like a band, essentially, this kind of normal modes, where you have K on this axis, and if you have rotational invariance, then this it will be simply depending on mod K. Again, rotational invariance is something that emerges out if the laws of physics are by themselves rotational invariance. Again, you are expected to have a quasi-rotational invariance. So even if you break translation invariance by some discrete group, it's still almost protected, because what happens is that if you know in a crystal or in you will have the momentum conservation is almost there, but up to a Brillouin vector. So if you should have K1 plus K2 equals K3 plus K4 plus a Brillouin vector. And these are often called Umklapp processes because it is so when you so basically it means that as a phonon mode has to absorb extra thing. So that those things are possible, but again these are only small effects. To a very good effect, to a very good approximation, even in a crystal, momentum is conserved. So basically you have something like this. You have mod k, and mod k is the thing, and you have this dispersion relations of this mode. And on this side, I would plot omega a k. So for a is equal to 0 mode, something like this, and e is equal to 1 mode would look like that. You have a tower of this kind of dispersion relations that are related by k, mod k. So essentially, this is a kind of picture, and therefore you can go back to this Hamiltonian now, which I wrote down. H is equal to sum A half QA dot square plus omega A square QA square, and this I can rewrite as d cube K and sum A, which is this so-called things, and then write it as half QA dot K square, right, plus omega A K, there is a dispersion relation of the mode, and QA K square, right? I simply put in the A, so sum over A becomes continuous integral over K, okay? And I should also put some 2 pi q because of some of the definition of this thing. And if you, at this point, I would like to just
the summation the summation over A and K.
Small a simply are these bands. So each of one of them will have some dispersion. So this is basically massless, and this has some mass. So what I want to say is that typically this omega a k square would look like this. Omega a mod k would look like this, would look like some ma square plus half, sorry, yeah, ma square plus v square k square, where ma is of course doesn't have the proper dimension of. Okay, so here I have to put some h bar or something like that, or maybe yeah, I would yeah. Okay, so maybe I should write it something. Okay, what I mean to say is as follows. So if suppose if you have somehow relativistic symmetry, omega a square has to be equal to ma square c to the power 4 plus plus something, right? Plus square root, if you wish, or no, sorry, I've already put the square here. But p is equal to h bar mod k, right? H bar mod k. So this will become square root of h bar square mod k square. If this is dispersion, if it is relativistic, again, but I'm saying we want to generalize it. We don't know if it's relativistic. For the moment, it's not necessary that you have Lorentz symmetry or anything. So I would just simply say it is starting. I would just simply, for the moment, parameterize it as something like m naught square, where m naught doesn't have a dimension of mass, but some other the right dimension that's necessary. And omega a would be equal to, sorry, let me write down a general relation. Omega a is equal to m naught plus some v mod k, okay, plus some higher order terms. Okay, for the moment, let me just write it down like this. Okay, so this is so this is how the dispersion relation looks like. And in general, if it's a non-relativistic theory, it will look like this. So this is something that you have to substitute here, and then you get this dispersion relations. Okay. All right. So let's try to see how the how does it look like if you, so what I can do a Fourier transform now. I can define something called QAX. It's a field, what I call the field, and this is simply dqk by 2 pi q e to the power I k dot x times qa mod k. Okay, so this is something I can call the field. Of course, this is a vector field, as you see, right? It's a vector field. And but then what typically happens is that you can further break down the field into something like a parallel and a perpendicular component often. So what you can do, you can say that QAX is equal to, or maybe at the level of QAK itself, you can say that a part of it is irrotational and something that is, so what you say is that it is QA parallel K hat plus QA perpendicular K, where you simply decompose this thing, something that is parallel to K and something is perpendicular to K, right? Now, this object that is perpendicular will satisfy K dot QA perpendicular is equal to 0, right? And in real space, this means that this object is satisfies, if you take the Fourier transform of this, right? This satisfies is divergence free. So this is essentially Helmholtz theorem. If you have seen it, if you haven't seen it, that's fine. And this is proportional to K hat. So you see that K cross QA parallel has to be equal to 0 in this thing. And this means the curl of this object, when I define QA parallel is equal to QA parallel K hat, then the curl of this object, when I go to real space, when I do the Fourier transform, is 0. So you can always decompose any vector field or any vector field QAX as something like is divergence free and something that is curl free. This essentially, and this is a unique decomposition that's obvious in Fourier space. Well, I mean, you're assuming that all of these things have a very well-defined Fourier transform and all of this. So if you don't follow all this, it's fine. This is basically basic. Have you heard the Helmholtz theorem before in electrodynamics? Have you seen it before this way? Why you can always decompose a vector field into something that is divergence free. So this is the part that is divergence free, and this is the part that is curl free. And this is actually the basic idea about electrodynamics. If you have
gauge like scalar field and vector, is it part of that? Like you have curl of A and del and scalar field phi, even they are divergence free, and one of them is divergence free and one of them is curl free. So
no, the application electrodynamics is as follows. So what you do is you decompose the electric field, for example, into some part that is determined by the static charges, or not necessarily static, determined by the charges, and something that is related to some freely propagating objects, like by radiation component, right? So the radiation component will be divergence free because it's not determined by the charges. So E is often decomposed into something E electrostatic, say, or not necessarily electrostatic, some E plus E radiation. So you have this equation divergence dot E is equal to rho by epsilon naught. So in Fourier space, this becomes K dot E is equal to rho K by epsilon naught, right? Now this part K dot E is this part is only determining, so but K dot E perpendicular is 0, right? If I take this component that is in Fourier space perpendicular to K, that would be by definition 0 because K dot that is 0. So it will only determine the E parallel part, right? the irradiation part, which is the Fourier transform of this object, the perpendicular component, the irradiation will be perpendicular to K. You remember one thing, like for example, why the photon has, why there's a, when there is, so you see that if you remember, the electric field is always perpendicular to a direction of propagation. If this is K, the propagating field, a propagating electric field will be always perpendicular, will have a polarization that is perpendicular to K, and that comes from here, right? And this radiation component would have parallel components to the direction of propagation, and it has two independent numbers because it has to be parallel. Whereas this component, the parallel component, will be determined by the electrostatic potential. So there is no free number there. So that is the reason. So if you have seen this is application electrodynamics of this theorem. You haven't seen this before.
Sir, I would have seen the decomposition, but no one coded it as Helmholtz theorem before, because I've done radiation stuff, but and I must have seen the decomposition, but I don't remember it as Helmholtz theorem or anything.
Yeah, but this is basically Helmholtz theorem because that's how it's obvious in K space that you can decompose something into parallel to K and perpendicular to K. And the part that is perpendicular to K will trivially satisfy K dot this thing in Fourier space. This simply means divergence is 0, right, of this part. So this part would be so the radiation part would be this perpendicular part, which has two independent components because it has to be perpendicular to K, and this part will be this thing. So this is often called transverse, and this is called longitudinal, and this is called transverse. Okay. So actually, we will try to be very. You can write down the. So if you look into such a longitudinal component, it basically behaves as a scalar field with respect to rotation, not scalar with respect to all kind of Lorentz transformations. I haven't assumed Lorentz invariance. It's scalar with respect to only rotation. So in a way, you could, the analog of it would be that you think of, instead of talking of the electric field, you talk of grad phi, right? And you only write your equation in terms of phi, right? Instead of writing it as grad phi, because it's obvious that you would be able to write this parallel component because it's proportional to K as K of something, right? K E by mod K. And this is what you can call phi, for example. And you can write down an equation for this. So essentially then, if you look at, you will always find a scalar component then, that would be the easiest component, and then we'll build some perpendicular components. So if you see that this corresponds to, if you look at a material, for example, there are these elastic waves, or if you look at, for example, a fluid, the longitudinal component is simply the sound wave, and the transverse components are the shear waves, right? Shear waves have this dispersion relation, omega is equal to minus I t k square, right? If you remember, and the sound waves has this kind of dispersion relation, VSK minus I gamma k square, where this is the sound attenuation. Have you seen all this before? I mean, you must have seen it because you are in from mechanical engineering. This is very basic. And there's an analogous thing for elastic medium, like it's a solid. There's always some, okay. So for in case of elastic medium, there is a sound component here too. There's propagating component. So in a solid, the shear waves are also propagating, unlike fluid. If you use Navier-Stokes equations, so that's the main distinction between solids and fluids. But actually, it's a continuum. You cannot really distinguish a solid and a fluid that easily. Sometimes there's a continuum. But all of this thing is very irrelevant for what I'm going to say right now. So this is just simply a caricature to say what you can do is that you could then go back here, right, and write it in terms of field, which is simply the Fourier transforms of this. So let us take the first term, for example, what happens if you do that. So let us take the first term, which is d cube k qa dot square. What happens if I write it in terms of x, in terms of Fourier transforms x? Let me suppose that this is a scalar for the moment. So because I'm taking only a longitudinal component. So obviously you see that qa dot square, I can always write it as qa longitudinal square plus qa transverse square, right? This is a vector and this is a scalar, rotational scalar. So this becomes only a square without any vector because there's a k hat here and k hat dot k hat. It's simply because q is nothing but q longitudinal plus q transverse, right? Because I have decomposed in Fourier space like that. So in Fourier space, that's obvious. So have you ever anybody of Percival's theorem? So Percival's, I don't know. Let me ask you if you have seen this before. So if I take a Fourier transform dk phi k square mod phi k square, that has to be equal to dx or dt. Okay, if we write it as in terms of x. Here we are using some normalization, so it is 2 pi here, dx mod phi x square.
Yes, sir, we've done
Have you
this.
seen this? Do you know the proof?
Yeah, like I mean, you take the Fourier transform statement and just phi k star you write, and you just like just basically
and
write
then
down the
you use
definition
that.
and prove it.
This is rather easy. I ask you to recall it, and therefore it turns out okay. There's a dot. It simply turns out that the first term d cube k by 2 pi q qa dot k square can be written in terms of the field, which is d cube x qa dot x square. So it becomes a field, it becomes a classical field. And often people just change the, so for the Fourier transform is often written in a different way. It's called phi a dot kx. Because the Fourier transform of qa, I can call phi a x, right? This is the field. And the next term is simply is easier. So suppose if you have omega naught square, k square. So then it becomes like this. So I can write it as ma square phi a square. That's the first term. But then omega squared will have this other terms like ma, then phi a, v dot grad phi a, some term of this kind. If I go to Fourier space, and then there will be ma, something like v dot grad phi whole square. Sorry, there's no ma then. I'm just simply expanding omega a is equal to ma plus v dot k. And if I do that, it will look like this. Sometimes, okay, so if you have rotational symmetry, v should be simply so this is scalar, it will be v mod k, and in that case you will have a phi. So here, the first term will become a total derivative, so you can forget that. And the next term would be this, simply this. So the final answer would be something like this. Okay. So this is what you will get. And this is nothing but the equation of a classical field, of the Hamiltonian of a classical field, which is dx square phi dot square plus m square phi square is a half overall, and plus d square grad phi square. Does it require more explanation? For example, why I get grad phi? Because k phi mod k square phi square integration over k is nothing but, again, k phi is nothing but grad k. So grad phi becomes k phi in Fourier space. So this, again, using Parseval's theorem, this integration over x, grad phi square. So this is how I get this field now. So Hamiltonian of a classical field comes up, right? This simply comes from the normal modes. Are you with me now? Because these terms, there will be a second term which involves only one derivative that actually will be that is a total derivative. So that will integrate out to 0, and you only need the next term. Okay, so that's how it comes about. So this is how you can get a field describing. So for example, if you take the universe and I want to compute some mode that describes long perturbations of the universe, I can describe it as a scalar field, for example. So, and I can describe I take anything, I can describe it using a field theory. And this is simply a classical argument. Okay, I've not even gone to a quantum argument, right? So now the point is, if I want to quantize, or now of course this description of a field will not be very good, right? If I go at very short scales, which are less than the scale of inhomogeneity, or less than the scale of inhomogeneity, if I resolve the system at much shorter length scales, then it's not a very good description. So any field theory has some kind of upper cutoff implicitly. So in a way, if you go back to this picture and I look at this K, this momentum K, this momentum K has some natural cutoff, right? So this has a natural cutoff, which is essentially the wave number corresponding to, it's a wave number that will correspond to something like some L inverse. Well, L is the scale of inhomogeneity. So there we will have some natural cutoff in the field theory. But however, if you look at a fundamental theory, it may or may not have a cutoff, right? It might say break down at some Planck scale or some scale where space-time becomes a bad description. You have to replace space-time by some quantum space-time or something like that. So it might be that for a fundamental field theory there is, but there are many fundamental theories which admit a fundamental description all the way to any length. Like one example is QCD, quantum chromodynamics. That's one beautiful example where you can actually take the limit L inverse to so L can be taken to infinity, so there is no length scale. So sorry, I think I wrote it wrongly. It should be proportional to L, right? Because L or some, let me put some kind of lambda. Well, lambda is some ultimate.
Length inverse only, right? Because this K is like length inverse.
Yeah.
Because wave number is 1 by lambda, so 1 by length.
Yeah, exactly. No, you're right. So it's L inverse. So L can be pushed to 0. All the way it can be put to 0. So this means that in QCD you can do it. In many fundamental quantum field theories you can, but not in quantum electrodynamics, not in standard model. So this is why people believe that standard model cannot be the ultimate theory, because simply because you cannot take the limit L goes to 0 there. You have to always have a fundamental cutoff, and there's a natural such cutoff. So we will see in the standard model or in quantum electrodynamics. Okay, so but that will require much more advanced concepts. I cannot simply go there, but for the moment, all I'm trying to say is that for a material, there's a natural such cutoff. It's simply the scale where you see the structure of atoms, or where quantum chemistry becomes more important. So their quantum chemistry is like an upper cutoff, where you have to use full chemistry to describe the material. Like you have to see how the atoms are bonding and stuff like that. But beyond that steps, but if you look at scales which are larger than that quantum chemistry length scale, if L is larger than that, then you can simply use a simplified field theory to describe the material, right? But then you know that this cannot be enough, right? You will also know that this cannot be enough. You should have some more corrections to that, right? D cube x there should be phi dot square plus n square phi square plus v square grad phi square, right? And plus you also have interaction of normal modes, right? Normal modes can interact, and if you expand the potential and write it in terms of normal modes, that's what I was doing, right? There was original potential, and at the quadratic level, it is simply some qa square omega a square. But then there are some higher order terms, which are, for example, quartic, or something like, originally it is something like qa, qb, qc, lambda abc. I should get quartic, some terms like that, right? And also some higher order core. So these should be reflected here in terms of phi cube, as simple as that. Some lambda phi cube and so on and so forth. So because it comes from expanding this potential, that's all. Okay.
So for the harmonic potential, it's first three terms, but if you have other interactions besides the harmonic, you're saying they might be.
Yeah, so I'm just going back to the original Hamiltonian. It was only in terms of these particles, xn dot square. You can always write it as sum of normal modes because it's an orthogonal transformation, right? You can always do some orthogonal transformation and write it as this normal modes. Okay, so what you're doing, you are simply, okay, so okay, let me go back to this thing. So what I was doing originally, I took this vxi, x1, xn, and wrote it in this way. It is some constant v naught. So when I'm writing it around this potential xi is equal to xi naught, it will be some v naught, right? Plus some half some a omega a square q a square, right? So remember, there was this can be written in terms of orthogonal. You say, I mean, you can, so this, you have to simply take this xn's, x1 to xi, and so you see that there was this, so originally it was vij xi minus xi naught times xj minus xj naught. So there would be no linear term because it's a critical point. There's no linear term. I only have the quadratic term, right? Now this I can diagonalize as a matrix. This can be diagonalized, and if I diagonalize it, I would get some omega a square q a square.
So you're saying, like, if you have a collection of n harmonic oscillators, you'll get cross terms like vij, xi, xj. If you write down the Hamiltonian, but
no. Wait a second. I'm not doing it. No. You're getting it wrong. So these term. So just take the potential of n particles, and they have a critical point at xi is equal to xi0. So the first term, if I expand around a critical point,
any
right,
general potential, you're saying?
Any arbitrary potential. If I take if you expand around, it's just a multivariate calculus. This is very basic, like analysis. It's a multivariate calculus. So x1 to xn, xi is equal to xi0. The first term is simply the minimal value, and because it has a minimal value, it will not have. It's a multivariable calculus. Okay, you take a function of n variables and you try to expand it around its critical point.
Yes,
right?
sir.
Yeah, and then there will not be any linear term, right? The first term will be simply vij xi naught times xj naught, right? And this is something that I can now diagonalize, right? I can do a linear transfer. I can do some orthogonal transformation because vij is symmetric, is a symmetric real matrix. I can always diagonalize it by some orthogonal transformation. And if I do that, it becomes omega a square.
So it's something like decoupling oscillations.
Haven't you seen this in a basic mechanics course already? The fact that everything
Yes,
can be written as normal.
Yes, sir.
So I don't know why it is so strange. So Vij is a okay. I'm just writing it. I should have put more indices here because it's a it is a vector. I should put another index, a vector index. But okay, you understand what I mean. So Ij would be, if you want, I can put that. Actually, what I mean is, okay, anyway, I think you will be able to generalize it. So I just, because these are very basic things, I will just simply go for it. So Vij is a symmetric matrix, right? So it can be diagonalized, by orthogonal transformation. And when you do this, it becomes a matrix which has omega A square, omega 1 square, omega 2 square, like this. And it's positive definite because it's a critical point. Of course, it can be a saddle. It can have something like this and a saddle direction like this. So, but this is not a place where I can, so then it will have some positive and negative direction. But this is not a place where a system can get stuck. A system can only get stuck somewhere if it is positive definite everywhere. Well, it might have some flat directions too, right? That's also possible. So that will give rise to massless fields. So you have omega 1 square, omega 2 square like this, okay? That's all I'm saying. And now when you, and these are basically some orthogonal transformations, and they become QAs. So O times X is equal to Q. If I actually assume rotational symmetry, it will not have any other such index. It's an extra assumption, if you wish. Okay, anyway, so now what I do is as follows. So so then because Q is equal to OX, where O is some orthogonal matrix, so half XI square has to be equal to simply half QA square. Sum I, and here is sum A. Because these are related by orthogonal transformation, right? The mod of a vector will not change under orthogonal transformation. So this is what I used, right? But now you see, if I go to quartic order, if I expand it, right, V, there's a V3 term, if I expand around a critical point, which is simply Vijk and Xi minus Xi0, Xj minus Xj0, and Xk minus Xk0. Okay. So this I should be able to write as lambda ABC, again by doing orthogonal transformations, right? I will be able to write as lambda ABC, QA, QB, QC. Right? And now if I go back, you see that, okay, I have all these dispersion modes. So somehow I take only the lowest one, I retain only this, and this becomes a field, right? Phi X. So I will call this a field phi AX, and this will be a field phi BX, and so on and so forth. Each will have a mass term, which is simply this. This mass term is something that is appearing here in the first sum, right? When I write it down, and similar, there is also a V. It will be an A. But what I'm going to say is that suppose you ignore the higher order terms and you simply retain the ABCs that are self interactions only between this, right? So you will get something. So you will basically get something that is d cube x phi x cube. Now, you might ask that why it is local, right? That's a good question to ask. So answer to this is that again comes from preservation of translational invariance, basically. So in general, it need not be local. I mean, in principle, this can be when you write it in terms of, so let's see a little bit detail what happens. So if I write sum A, lambda ABC, so basically lambda, I assume lambda is independent of K1, K2, K3, roughly speaking, or okay, for the moment, let's assume that. And then what happens is, so I can write it as d cube K1, d cube K2, d cube K3, and lambda. So lambda, basically, the idea is that you simply also expand lambda in K and retain the first term. And then the higher order terms, you can absorb it in higher order fix. So for the moment, you just simply have lambda. And if I keep lambda and I do this, okay, let me explain this and then see. But then there is a delta cube K1 plus K2 plus K3. Okay. So this is actually equal to nothing but lambda d cube x pi x cube. Because of presence of approximate translational symmetry, which gives you this K1 plus K2 plus K3. And that's also obvious. This equation is translational invariant, right? If I change x to x plus lambda, then this doesn't change. This because I can absorb it into the redefinition of this thing. So this is translational invariant because it's invariant under x to x plus lambda. So if you don't believe me, you can try to go back from here. So let us try to see whether this is equivalent to this. So I take what is phi x? Phi x is dq k e to the power I k dot x, k1 dot x, I put phi k1, right? And I put d cube k2 e to the power I'm writing phi x cube in this way, right? I'm writing phi x cube twice. All right. But then there is an integration over x, right? Which I can do first. If I do the integration over x, I have to integrate this, this, and this, right? So I have to do integrate d cube x e to the power I k1 plus k2 plus k3 dot x. And this integration gives me delta cube k1 plus k2 plus k3, right? So if I substitute it back here, then I can just integrate out one of these things. Or okay, if I substitute this back here, I get simply lambda d cube k1, d cube k2, d cube k3, right? Times the overall factor of 2 pi to the power 9. And then I have, okay, there are these factors of 2 pi cube, which I forgot to write. And then there would be phi k1, phi k2, phi k3. Okay, this is a Fourier transform. I'm abusing notations by denoting the function and the Fourier transform by the same phi. If you wish, it should become q. If I have many, I should have written it as q. Okay, so is the step clear now? So then what I can do, so now let us go back to this lambda. So what I had, so in general, lambda would be a function of k1, k2, k3, right? But what I can do, I can simply expand it. And because I'm having only small k, the assumption again is that I don't have large gradients, I will have small gradients. And because I'm always at small wave numbers, which means I'm always at large length scales. I'm not resolving the system at very short length scales. So in that case, if k1, k2, k3 are all small, I can expand lambda to be something in power series in k. And each of these things will become then derivatives. At higher orders, it will be derivatives of the fields. Now, if lambda is a constant, right? And so the first term, as I said, was lambda qa, qb, qc. And I assume some overall homogeneity, overall translational invariance, I will automatically get this factor, delta cube k1, k2, k3. And then if I expand it, I get this field, right? I get the next term in my field. So that's the logic by which I can say, if I'm expanding in K, if I'm doing a systematic expansion in K. So there's a similar logic that appeared here also when I wrote the first term. Of course, omega square can have higher order terms in K, right? And that would mean that I would have higher derivatives here. There'll be not only grad phi square, but say grad square phi square, Laplacian of phi, then whole square of it. Everything is possible. So there would be higher order terms also. But I'm simply truncating at a leading order in K. And so I can systematically take into account. So the main point is that I can write everything down as a field theory, right? By assuming that there is some kind of homogeneity or translation invariance that emerges at long lengths. There are ways also to go beyond, not assuming. So you can also assume that there is momentum is relaxing. And for that, you have to do something little bit more interesting. You have to include some dissipative terms. But it becomes a little bit confusing. How will you introduce dissipation in quantum mechanics? It's possible, and this is something that is possible in the Schwinger-Keldysh contour. If possible, I will try to show you how you can do that, but it would be a little bit more advanced concepts needed. But it's a
What
very,
Lorentz invariance?
sorry?
Lorentz invariance.
For
We
the
need-
moment, I'm not assuming Lorentz invariance. I'm not. For Lorentz invariance, this V has to be equal to the speed of light, but it need not be, for example. Okay, so
Excuse me, sir.
yes, ask me.
Yeah. Could you go to the before where you have expanded the Fourier transform? Yeah. So there will be also a term 2MA into V into mod K into.
Yeah, I said that. You see, I already said that there will be a term which is MAV grad phi, right? As you said, it will be grad phi. And then, okay, one way to write it is V dot grad phi times phi, okay? Where V is, I assume that V is, okay, there is, okay, you will get a term of this kind, right? But V is
Yeah,
a
yes.
constant. And therefore, this is basically a total derivative, which will integrate out to 0. So V dot grad phi times phi is basically V dot grad of phi square. And V, you can take V outside of the integral, and this becomes a gradient of something that should integrate out to 0. Okay. All right. So, all right.
it
So
will be a
I
boundary
think,
term, you're saying?
huh?
Are you saying it will be a boundary term or something?
It will be a boundary term, and the assumption is that the phi's are going to decay at,
Okay.
actually, without that, you cannot even apply Helmholtz theorem and everything. There's Helmholtz theorem has an assumption that phi's in real space, it decays. And also application of Percival's theorem applies all. So there's always an implicit assumption that phi is going to decay at infinity in such a way that you're able to justify all this manipulation. Okay, so there's a famous example where Helmholtz theorem is violated. So you can, so what basically you're saying that Helmholtz theorem basically says that you can write any vector field as grad of something plus curl of something. That's actually okay. Again, so basically what you can do is you can. What does Helmholtz theorem say? That Helmholtz theorem say that, as I said, that you can write any vector field as V1 plus V2 such that divergence of V1 is equal to 0. This is unique. And curl of V2 equals to 0. Now, divergence of V1 is equal to 0 implies that V1 is actually curl of something, curl of some A. And curl of V2 is equal to 0. It implies V2 is equal to grad of some phi. So that implies that you can write any V uniquely as, that's kind of obvious, right? Because again, in Fourier space, if divergence of V1 is equal to 0, it's orthogonal to K. And if it's orthogonal to K, you can always write as K cross some anything, K cross something. So, but okay, this is not unique because you can always write, you can always put a longitudinal part. So it always has this non-uniqueness of A and phi are non-unique in a way, but you can always do that. But there is an example where you can, well, this theorem is violated, where you can write that vector field both as a curl of something and a grad of something. Do you remember some example of this kind? Well, that's a dipole field. Dipole field, or electric dipole field, and a magnetic dipole field basically looks the same. But you see, the magnetic dipole field can be written as a curl of something. The reason it is violated because there is a singularity. It's not the vector field is not uniform everywhere, but there is some singularity. So so this is what, so you see it's a little bit tricky always not to apply all these theorems. So there's always some assumptions that are put in. It's just a by the way. Anyway, so yeah, I think you should go back and get your basic stuff right. Like this is very important because these are very elegant and beautiful things. And yeah, but anyway, along the so basically you see quantum field theory is a crown of physics. When you actually go there, you will see that you have to go back to the basic stuff and learn it better. Actually, it's very interesting that we will see soon that quantum field theory also makes you understand high school physics better, like why something like Johnson noise is true, why the noise, but thermal noise is related to the resistance. This is basically a fluctuation dissipation relation that we will see soon. That comes out very elegantly from quantum field theory. So it's a very beautiful thing that it's really a crown of physics. And while you see it, while you do it, you see that you can connect to all the things that you know earlier in a much better way and more elegantly. Anyway, so the basic point I hope I got you is that if you assume that there's a translation invariance, that say momentum is conserved, that means that the interactions are local, okay? Which means that you see that the crucially this d cube x pi x cube, the thing is completely local in x. It's not a bilocal object, like it's not something like, it is not d cube x, sorry, this is terrible, terrible, terrible. It's not something like okay, what I meant to say is it is not something like this, like d cube x1 for d cube x, d cube y, d cube z into some f x y z times phi x, phi y, phi z. It is not like this, right? It is not like this. It's rather a local expression, which is very important. And this locality is a very important point of quantum field theory, right? So what I'm trying to show you is that you take any system, and if you assume there is some homogeneity, that some kind of translation invariance that emerges, like in the universe, like at 100 megaparsec, is 100 parsec or 100 megaparsec, right? I think it is. Are you sure the scale of homogeneity is 100 parsec? I think it's 100 megaparsec. If I remember correctly. Okay, Arcanus have seen written Hessian matrix for this matrix is true. This is called the Hessian matrix. It is often called the Hessian matrix. Yeah.
So 100 megaparsecs, you're right.
100 megaparsec, exactly. So if you look at that kind of a huge length scale, right, you will see homogeneity coming up. And at that scales, if you are looking at k smaller than, or wave numbers smaller than that scale, then it will be you will be able to apply, or it will be correct thing to say that there will be translation invariance, and therefore you should be able to describe the system as some kind of a local field. Obviously, if you are resolving at scales lesser than 100 megaparsec, then this assumption is not true. You have to resolve phi x cube further into some kind of inhomogeneous pieces or non-local. The theory will become non-local at that length scale, but otherwise it is true. It's a local. It's very important. This locality is a very important part of quantum field theory, actually, to be able to, because the cluster decomposition and everything follows. It's very much important. The cluster decomposition principle holds only if you have locality in your theory. But as I said, you can always do that, because you can always expand lambda and okay, so that is something that you can always do. And even if it is not conserved, even if this locality is violated in small ways, you are also you will be able to incorporate that in quantum field theory formalism too. Except that I would need some more tools to do that, because I need to then introduce momentum relaxation or dissipation, because momentum, how momentum is lost to a path or something, that I need to introduce. But for that, I have to introduce some. I will try to do that. I'll hope to do that maybe by the end of this course. It's completely new techniques that have come up very recently to be able to do such things. Okay, so let me go back to what I was doing before. And all right, so now let me go back to my story. Okay, my story is now that, okay, my Hamiltonian is simply the classical Hamiltonian. If I just keep only the lowest branch of this excitations, I would be able to write and so on and so forth. Of course, there can be terms also of this kind, like lambda phi grad phi square. There can also be terms like that, and so on and so forth. So all of this, so these are what I call interactions, right? So now the idea is as follows. Let's go back and think in terms of the original things. So the first two terms I would be able to write, if you wish, in terms of k, right? D cube k. And now I call it q dot square. Q is a function of k, right? Q dot square plus v square mod k square q square, right? That will be the first two terms. The second term would be plus d cube k1, d cube k2, d cube k3, lambda phi k1 or qk1, qk2, qk3 into delta cube k1 plus k2 plus k3. And there is overall factor of 2 pi cube. There's an overall factor of 2 pi to the power 9. Okay, so this is how the Hamiltonian would look. But if I just look at the first two terms, it basically looks like a harmonic oscillator, right? Where omega naught is, okay, there is plus m square q square 2. Omega naught square is simply m square plus v square mod k square. Except that this omega naught has some omega k as a label k2. So you see that basically the first two terms can be written as harmonic oscillator. And the next terms can be written also in terms of the harmonic oscillator basis, right? But you see, okay, so now let's just look at the first term. So the Hamiltonian, if I rewrite again in terms of q and mod q, the first Hamiltonian, I should be able to write as in this way, d cube k omega naught k a dagger k a k. After if I take this particular term and write it in terms of this, so this is essentially p squared by 2 plus x squared by thing. So if I use appropriate normalizations where I can absorb the m or something, so okay, I leave it to you to figure it out. This is not that hard. You can always define a dagger. Okay, I will show you explicitly later. So you can always, it's very easy to see. I mean, it's just simply, because each k mode is independent, right? For each k, you can then quantize, you can just simply write it as some a dagger ak, right? And where all of these ak1, ak2 would be equal to 0, because different a's and a daggers will commute, and similarly for a daggers. But a dagger k1 or ak1, ak2, a dagger k2 will be equal to simply delta cube k1 minus k2. So only when k1 and k2 are the same, you would get unity. Otherwise, you will get 0. So this is how. Sorry.
Half. Are you just ignoring?
There is a half factor.
No, sir. Like
for omega naught plus half.
Oh yeah, half. Yeah.
Let me write it down. Omega naught omega k. Sorry. There is something. Yeah. Sorry, the half is. Sorry, what I'm writing is stupid. Let me read it this way. H bar omega k a dagger k ak plus half. Right? So I can always do this. So this is the first important statement. I would be able to then do this. Now, the interesting part is that if I look at these term, is simply a number. It's not. There is this. There's a ground state energy of the system, which is simply dq h bar omega k, and there's an overall half. Because in the ground state will be where all of these AKs annihilate the ground state. Now, this ground state, if you go back to the original particle system, x1, xn, is a highly non-trivial wave function, right? x1, x2, xn. It's a highly non-trivial wave function. It's not something like a vacuum or anything. It's a highly non-trivial, highly correlated state. But when I write it in terms of these oscillators, right, in terms of these Qs, so A of k would be nothing but some linear combination of Qk and Qk dot, right? If you remember, that's how we wrote F combination of x and p. If I write it in terms of this Qs, it annihilates this. So basically what I'm doing, instead of solving a differential equation or Schrodinger equation, I'm going to algebraify, right? So all the input I need is a classical input. I just need to know the potential. I need to look at the Hessian of the potential at the critical point, diagonalize it. Once I do that, I would get the omega square and basically go to some continuum limit and get this omega of k by some classical computation. But once I have it, and basically if I know, and I can also write down the interaction of everything. Basically, I should expand around the critical point. The first term will be the Hessian. Then I would get like cubic terms and write it in terms of this lambda that I found out. So all these are classical data, okay? So that's all classical data. So I need to do those computations, but that's an easier computations, much easier than solving for the wave function of like 1 mole, where the 10 to the power 23 atoms. Like I don't want to do this. I don't want to solve the Schrodinger equation of these guys. It's an impossible task. So I can go to the language of field theory now, right? And I know at the leading order, I know what my what is it, right? And this is my ground state energy, half dq k h bar omega k. Now this is typically, if there is no cutoff here, right? If there is no capital lambda that does some cutoff, where lambda is proportional to some L inverse, and L is on some microscopic line scale, beyond this thing breaks down. This will be some infinite number. It's a huge number typically, right? It will be a huge number, and it is supposed to be huge because it is. But nobody cares about this number actually. Typically, this number is divergent if you take lambda goes to infinity. So what you do is,
we were expanding around small k, right? Or something like that. You were doing expanding the
if I integrate this, so typically what happens is if I just keep the leading order terms like m square plus k square v square, right? This is a divergent integral, because if integral of dq k over k square, just the first term, right? M square dq k, that's a divergent integral. That happens because, okay, omega of k could be a very nice function that actually gives rise to, because at very large values of k's, you cannot use this, right? It might have some kind of a, it will like fall off. It will have something like 1 over mod k behavior. But this is not what we're interested. We are not interested for large k, because we're only, the field theory itself is valid for k less than some lambda. So it's not necessary for me to go to very large k. If I just retain only the small k terms, this is a divergent integral, right? But who cares? I mean, energy of the ground state is not an observable. If I'm at only, like if I can only have some low energy observables, I can only see how the change in energy from the ground state, but not the ground state energy itself, right? So basically, the standpoint is simply to forget this plus half factor, simply because I can subtract it out. I do some subtraction. So this is the first example of some subtraction of infinities. So you basically subtract it out because and put the ground state energy to 0. That's something that is you simply do for practical reasons, that that this half is no longer required. Okay, now what do we get, right? So if you want to create one particle state, we should have this kind of states in the theory. It's simply I create a dagger K vacuum and I get some one particle state out, which I call K, right? I can create two particles. So now why I call it particles, right? That's very important. So suppose I do like this, I create a dagger K to the power N, and then we saw that these are normalized states, 0, right? So basically I create a state which is, I call NK. So there, right? And this NK has energy. If I look at the energy of NK, what it will be? It should be simply h bar omega k times n, because h is simply, the reason for that is that, okay, let me write down h is equal to d cube k, a dagger k, ak, times h bar omega k. So if I act, so I act this thing operator h on some a dagger k naught to the power n on the vacuum on this state, right? Square root n factorial. Now, if I act this, so a will be commuting with a daggers, right? Unless and until k is exactly k naught. So for all k greater than k naught, I can move the a past all these a daggers because they commute, and it will annihilate the vacuum. The only thing that doesn't annihilate is simply a dagger k naught, a k naught, h bar omega k naught times a dagger k0 to the power n by factorial n 0. And this algebra we already did for the harmonic oscillator last time, right? This is simply the number operator acting on this, and we computed how to calculate the spectrum, and this answer is simply then h bar omega naught n, h bar omega k naught n times the state. And this state I call simply n k naught, which means that there is the occupation number, or the index is n, right? So now you see that we can easily give some kind of particle interpretation. Why particle interpretation? So firstly, you see that there is a dispersion relation of omega k, right? For each k, there's a continuous energy. And this is exactly like a dispersion relation of a particle. And this nk, and also the energy scales with the number of particles. So essentially what we can interpret this nk naught as a state with n particles with momentum k naught. Okay, but we can also build some other state, like say a dagger k1 to the power n1 by square root n1 factorial, a dagger k2 to the power n2 by square root n2 factorial acting on the vacuum. You can easily do the algebra again. What is going to be the energy of this state? And I call this nk1, nk2. So if k1 is not equal to, okay, even if k1, because a daggers all commute with each other, the order here doesn't matter, right? Because a daggers all commute with each other, it doesn't matter which order I write this thing. So the energy of this state, h nk1, nk2, would be simply h bar omega naught, or sorry, h bar times nk1 omega k1 plus nk2 omega k2. Again, it's a very simple algebra, because if I have a dagger A, all the A's I can just pass all the A's through. So you can do this algebra easily. Is it obvious? So again, because it's a dagger A, I just simply only the A, I can just pass A or through it unless one of the A's is equal to either K1 or K2. Now if it is equal to K1, then this is simply a spectator. I can always move this thing to left and right because it's again commutes. And so you can think about it and it's very easy to see. So in general, the energy eigenstates are simply so I write it as a set because for each K mode, I have to specify what is N, right? And this can also be denoted as a function. If K is continuous, I can even denote it as a function Nk. This is often called the occupation number basis. And this you see is normalized, right? With this. So basically what we will see, it's more convenient to use some other basis called the Folk basis, which is not the occupation number basis, but the Folk basis is not normalized. It's much more convenient to use that kind of a basis, but I will not talk about it today. I will talk about it later. But for the moment, it's an occupation number basis. And here you could define it like this. And the energy of an occupation number basis is very easy. H and K would be simply d cube K by 2 pi q H bar omega K and K and times. Is it obvious why? It's simple generalization of the computation that we've done. Okay, now comes the big thing. Okay, so you see that instead of solving the Schrodinger equation, what I did something rather simple. I simply went back to the classical potential of 10 to the power 23 particles, and I diagonalized the Hessian about a critical point, and that gives me this omega k. And once I get all the omega k's, I can know to a good approximation what are the energy eigenstates without even solving the Schrodinger equation. But here comes the point: the Hamiltonian is not that. So I simply call that Hamiltonian H naught, where H naught is the quadratic part, which is a dagger A times H bar omega. This is my quadratic term, but H also has a term, which is H is equal to H naught plus some interacting term, which is called, let me call it Hi, where Hi is lambda I cube x d cube dx, right? Now you see what is phi. Phi is essentially a combination of A and A dagger, right? Because that is essentially x. Is the x of my, right? So because yeah, so in this analogy, when I started with this thing originally, this original half q dot square, the q was behaving like the x of the, so this is half x square plus omega naught square x square, right? This is half x square and this is half omega naught square x square. So q is x and x is a superposition of A and A dagger. So this is actually what? Phi cube is essentially A plus A dagger cube. If it is A plus A dagger cube, I will get terms like A cube. It's a Hermitian operator. So I will say get a G A cube plus G star A dagger cube, because it has to be complex conjugate because it's Hermitian. And then I will also get terms which are A square A dagger and things like that, and the corresponding, and also I will get, yeah. So I will get all of these kind of terms. Even if I have phi to the power 4, I would get terms which are A to the power 4, then A cube A dagger, or A dagger A cube, something here, plus something A dagger square, A square, right? Plus Yeah. Yeah, and plus Hermitian conjugates of this guys. Okay, so I will get something of this kind. Now you see that if I look at these individual terms like a to the power 4, it did not conserve number of particles, because if I have a to the power ak1, ak2, ak3, ak4, right, acting on some nk state, right, what is going to happen? Is going to lower the number of particles at K4 mode by 1, K3 mode by 1, K2 mode by 1, and K1 mode by 1, right? Right? So I get terms in my Hamiltonian that doesn't conserve number of particles, right? So now you see that I have to pay a price. So originally I was starting with some Schrodinger equation where there were fixed number of particles 10 to the power 23, and particle number was conserved and everything. It's a non-relativistic system. But even for a non-relativistic system, if I have to simplify it to harmonic oscillators and go to this field theory like description, it's a much more simplified description. I need to pay a price, and the price is I cannot look into Hilbert space with fixed number of particles, because operators are going to lower the number of particles and is not going to conserve the number of particles, right? So this is the main thing. That this is the most fundamental thing. So in QFT, give up working with fixed number of particles. So this is why this is the price that we have to pay, right? But actually, so the way I told you is as follows. I'm trying to describe any form of quantum matter. I have to necessarily, the simple thing is to use a formalism like QFT instead of trying to solve n particles, right? But this is true in a non-relativistic restriction. But in reality, we have a fundamental Lorentz invariance in physics, right? Maxwell's laws are Lorentz invariant and things like that. It could be that Lorentz invariance is simply a manifestation of some low energy something. And if you really go into very high energies, Lorentz invariance is not a fundamental thing of nature, but there is little evidence for that. I mean, we get particles which are extremely, extremely high energy, and we have seen Lorentz invariance holding up to extremely high energies experimentally. There's little evidence to suggest such a thing is true. So Lorentz invariance is, in a very elegant way, must be a fact of nature, because there is some fundamental, there's only with such a Lorentz invariance, you get some notion of causality, right? Without that, you don't get a notion of causality. So if Lorentz invariance is a fact of nature, then anyway, we cannot work with fixed number of particles, right? This is something that we will see or try to understand why. There is no way we can work with fixed number of particles anyway. But forget Lorentz invariance. Even if you're trying to explain some non-relativistic physics of a material, and if we have to go to a simplified field theory description, then we have to give up on a formalism that keeps the number of particles fixed. We have to be able to superimpose states with different nk. So we have to live with some state psi where we have some something like this, like some vacuum, A0 vacuum plus AK is some, okay, I should not confuse this A with, let me call it C. C0 is just a number, plus something DQK, CK, K, right? Plus DQK1, DQK2, C, K1, K2, then K1, K2. So you see that all of these, which means there's only one particle in K1 mode, one particle in K2 mode. That's what I mean. Or maybe I should, if I'm writing in, I should really be consistent with the notation. I would say 1K, 1K1, 1K2, like this. So I have to be ready to work with such So you see the superposition of having no particle at all. But I said the vacuum is actually having no particles, highly difficult state, right? A psi of n part. One should not think of it as a trivial state. And then you have something that has one particle, and then I have one particle in. So I have to be, so there is no definite number of particles in such states, right? And such states are actually have to be, so in reality, such states are the right states to describe materials, where I do not have fixed number of particles. Because if I look at eigenstates of H instead of eigenstates of H, if I look at H psi is equal to E psi, right? Because H doesn't commute with the number operator, right? The eigenstate of the Hamiltonian will be of this form. H naught commutes with N, but H doesn't commute with N. So these are the correct states to describe the excitations of a material, right? So you will have something like particle-like excitations, which look like this, essentially, but they are sort of but they have a virtual cloud of other fluctuating particles around it. So that will be, so we'll see there's a notion of quasi-particles that come in still, and we'll see why it works out. So that's the first thing to keep in mind, that we have to be ready to work with such states. And these are the states that actually are the energy eigenstates of the actual material, because the Hamiltonian doesn't commute with the number of particles. But then you can ask is, why on earth I'm trying to do this? Why on earth I'm using the quantum field theory formalism to describe a material? Because I can simply diagonalize, right? Some big Hamiltonian of 10 to the power 23 particles, just go to quantum mechanics and do this. There's also a fundamental reason, because even if I'm able to diagonalize it, I won't understand the physics. So for example, what you can show is that, for example, these lambda 5 to the power 4 term is all that you need. Even if at low energies, if you have something like lambda to the power 5 term or some lambda tilde, these kind of terms turn out to be irrelevant at low energies. And this is a very deep statement. It simply tells you that, so now the question is why quantum field theory is predictive. In quantum field theory, if I write this, I will have lambda phi cube plus lambda phi grad phi square term plus some lambda tilde phi to the power 4 term plus lambda tilde tilde, let me call it some tilde here, tilde here, some phi square grad phi square term, and so on and so forth. I can have these kind of terms. What you can show that there are only a finite number of such terms which are relevant if I keep t greater than or equal to some, say, mu, and this is greater than or equal to lambda. So you can actually show that some of these terms are irrelevant. They're suppressed. Their effects are highly suppressed. And this is where comes the notion of renormalization group. So essentially it tells you that when you take into account all of these things and think of quantum field theory in a proper way, actually you should think of a different kind of description at every length scale, or at every, and this is the overall scale of observation. So basically it means your microscope is not looking at length scales L less than or equal to mu inverse. We are not looking at that kind of length scales. We are looking at, say, a fluid or flowing water. We are not able to resolve the atoms. We are simply able to resolve the flow. And then Navier-Stokes equations are good enough. So things like that. What I mean is as follows, that even Navier-Stokes or equations should be thought of as some effective field theory, actually. That's actually a very interesting thing that people have realized recently. So what I'm trying to say is that you have this kind of length scales, and then it's predictive because only a finite number of these terms are going to be relevant for your description. And this is why quantum field theory is predictive, because you only need a finite number of numbers. And this is not something obvious, right? It's completely, totally non-obvious statement. Because a priori, you would have, if I written in terms of, if I've expounded this very big potential, x1, x2, xn in terms of normal modes, and even if I assume translation invariant, emerging, I would have infinite number of terms. But it turns out this infinite number of terms are not relevant. Only a finite number of them are relevant, and that depends on the scale at which you're resolving the system. There's an ultimate scale, of course, lambda inverse. This is beyond which the field theory description itself breaks down. That will be replaced by quantum chemistry or something else. But at least below the length scale, you have only a finite number of terms at each level. So if you, of course, if you increase mu, number of terms that you may need to keep would increase. But up to a given length scale is only a finite number of terms that need to keep. And this is a feature, this is what I call effective field theory. And that's the basic crux why field of applying field theory to nature. Okay. So that's all for today. So I hope I give you a flavor that now that you are doing like the harmonic oscillator, we are talking of quantum mechanics. Now suddenly, why the transition to field theory should not be will be rather painless, right? Or because all of the things that we have learned or operator algebra can easily be carried on here. And because you can, and now you also see that why this n in the level n in harmonic oscillator can be rather interpreted as number of particles and things like that. Okay, so that's sort of I should end the lecture today here. Is there any question before I end today? Okay, again, in textbooks you won't find such kind of things, right? So if you so it is all implicit there, but it's never made explicit because you have to write the origin of field theory. It will take a huge space like this. So that's why many textbooks will skip it, but it's a class and not a textbook. So all right. So then let me end recording.